The definite integral, estimating with finite sums. Well, okay, when we start off a new unit like this, the titles sometimes have words in them that we haven't really covered yet. The definite integral. Hopefully by the end of this lesson, you'll have some idea what an integral is, and estimating with finite sums, what that all means. So it's another one of those titles that's a little mysterious when we start off, but we'll get the idea as we go along. Okay, as it turns out, there's two types of calculus. Up to this point, the main focus of our calculus studies has been on instantaneous rates of change, tangent slopes. Like if someone asked you about calculus and what calculus is all about, at this point you'd probably answer instantaneous rates of change. That's what really we've been doing all the way along, is trying to find those tangent slopes. And we've certainly seen a load of applications of tangent slopes and instantaneous rates of change. Now, that type of calculus is called differential calculus. That's what we've been doing up till now. So starting today, we've got to have a new word for the new type of calculus we're going to look at, called that it addresses the problem of finding areas under curves. And it might seem like, why in the world would we want to find areas under curves? And I'll just have to assure you at this point that it will definitely be worth it. That as many applications as we saw in differential calculus for instantaneous rate of change, we'll see at least that many under integral calculus. In fact, many people would argue that integral calculus has more applications. And so when we're finding areas under the curve, we call it integral calculus. Why do we call it integral? Well, okay, we'll get to all that. But for now, you can say, okay, when we're not finding instantaneous rate of change, when we're trying to find area, then we're talking about integral calculus. And it may seem that these two types of calculus are unrelated, but as we will soon see, they are indeed connected. So give it a little bit of time, and we'll see that these two types of calculus are very interconnected. Even though it's described as two types of calculus, you'll find out that there's some huge connections between the two types of calculus. That'll take a while to develop. So setting the stage, consider the following problem. A train moves along a track at a steady rate of 125 kilometers an hour. If the train travels for 4 hours, what is the total distance traveled? Well, okay, so we don't need too much calculations here. Because the train is moving at steady speed, finding its total distance traveled is not a big problem at all. You might be able to just do it in your head. You might not even need a little equation. I'll do it with an equation just to get the physics involved here. But distance is velocity times time. So we take the velocity of 125 kilometers and we multiply it by 4 hours. And we get 500 kilometers. It doesn't take much physics to stick with that example. Now, this is where the integral calculus starts to come in. Notice the distance traveled is actually the area under the graph shown below. So if I draw a graph, velocity and time you see there, and I say, okay, well, the velocity is 125 all the way along there, so it's a constant velocity, so straight line across there, and then I cut it off at the 4 hour mark, and what I get is a nice little area under there, and the area of that rectangle, well, its height is 125, and its width is 4. That's exactly what we calculated above. So we come to this conclusion that you could also do this question by finding the area under the velocity curve for the time indicated. Sort of an inefficient way to do it. It's very elegant, but for now, just stick with the idea that you could do it this way because you won't have to wait long to get the payoff here of why this is such a great way to do it. You'll see that in the next slide. So on this slide, focus on the idea that, okay, well, I guess I could do it that way. I could interpret this thing as a geometric problem and say, okay, we're doing an area where the height is the velocity and the width is the time, so that the calculation, area 125 by 4 of finding area, is the same as finding the distance. So we come to an important sentence, which is the area under a velocity time curve graph is the distance traveled. This connection could be made for any constant velocity and any length of time. So that's a handy thing to know moving forward. Now, if the velocity is not constant, would the area under the graph still give the distance traveled? And the answer is a gigantic yes. Now, there's problems looming. When you look at that, you're like, well, how am I going to find that area? Don't worry about that for now. We'll get to that right shortly. It will not take us long to be able to find some tricks to find the area under a strange curve like this. For now, we just go, okay, that area still represents the total distance traveled. And if you're skeptical about that, think about this for a second. If you take that area and break it into many small subintervals, each of those little subintervals comes close to resembling a rectangle, some more than others. But when you get those rectangles on there, each one of those is a little distance area, velocity times time. So each one goes velocity times time, and you're doing an area on each little piece, just like we were doing the area in the constant velocity example on the previous slide. So each of those rectangles represents the distance for that section, and if I add them all up, I'll get the total distance traveled. So I partitioned that time interval A to B into many small subintervals as shown below. Now, if you're looking at it going, well, some of those aren't very much like rectangles because the curve is changing a whole lot in that section, I totally agree with you, and we may have to go to some very small rectangles to get a very good estimate. So if these intervals are made small enough, the velocity over each subintervals would essentially be constant, and the narrow strips would closely resemble rectangles. You can be skeptical about that if you want. I think you should be skeptical about that. But what I'll say is they'll come close enough to rectangles that we'll get a pretty good estimate. We'll find out later we can make it an excellent estimate. But for now, if you're like, well, this is only going to give an estimate, I'm okay if you're at that part, at that level with your brain now where you're going, okay, well, it would be a decent estimate, but it wouldn't be necessarily that great. And we'll improve on that as we go along. So just as the total area can be found by summing the areas of those rectangular strips, the total distance can be found by summing the small distance traveled over the tiny time subintervals. So each of those little rectangles, or close to rectangles, will be a little area that we'll calculate. But each of those little areas is a little distance traveled, so we can add up all the little distances and get the total distance traveled by finding the total area under the curve. Now, hopefully that shows you why this method in the previous slide is so important, is to go, okay, first we establish that a rectangle underneath this curve represents the distance, and then we say, well, okay, we got a strange shape like that. We can break that up into a whole bunch of almost rectangles and add all those up. And again, don't get caught up in the accuracy part of it because we're going to deal with that and a half as we go along here. So this whole method is called the rectangular approximation method. It's basically taking a curve and breaking it up into little rectangles that can approximate the curve, and so that's why we call it rectangular approximation, RAM. So whenever you see the word RAM from now on, that little short form acronym, we're talking about estimating the area under the curve by using rectangular approximation. Some important points about this. The more rectangles we use, the better the approximation. So when you're looking at that picture on the previous slide, of course, many of them don't look like rectangles, but the more rectangles we use, the smaller each rectangle will be, and the more they will be accurate representation. So here's some pictures. If I were to use 4 rectangles here, you can see that those 4 rectangles don't do a great job of estimating the curve. There's plenty of extra area here that the rectangles are calculating that is not actually under the curve. But if I go to 8 rectangles, I hope you can see that the amount of area the amount of extra area that's calculated by the rectangles is less. And if I went to 16 rectangles, it gets even less. You can imagine if I went to 1,000 rectangles, I would still be overestimating the answer here, but not by much. And maybe you can see limits coming and say, okay, well, maybe we can send a limit and make the number of rectangles go to infinity. And if we do that, then we can get a great estimate of the area under the curve. Now, we can choose different points for where the rectangle will touch the curve. We could make the rectangles touch the curve on their left-hand side, and we'd call that LRAM. We could make the rectangle touch the curve in the middle, which would seemingly be a better estimate in some cases. And the height of each rectangle is determined by evaluating the function at the midpoint. Or we could do RRAM, where the rectangles are defined by their right-hand side. That is, the height of each rectangle is determined by evaluating the function at the right-hand endpoint of the subinterval. It all comes down to where you're going to draw the rectangles. And I'll do some examples so you can see how you're going to draw these rectangles and how it all goes. It's easier than it sounds, but actually getting the numbers is probably harder than it looks. So it's both easier and harder at the same time once you see the examples. Now, the question I want to ask here is, will LRAM always give an underestimate? If you look back up at the LRAM picture, those rectangles are all underneath the curve. And if you look at the RRAM picture, they're all above the curve. Now, then is it true that LRAM's always an underestimate and RRAM's always an overestimate? And the answer is no. That all happened because this particular function happened to be increasing the whole time. When it's increasing the whole time, LRAM will underestimate, RRAM will overestimate. But if you drew this curve the other way and made a curve that was reducing or was decreasing, you'd find that LRAM would now overestimate and RRAM would now underestimate. So you have multiple things that can happen here based on the curve. So I don't want you to prejudge each of these methods. Each one of them will do an okay job of estimating, sometimes over, sometimes under, depending on the curve you're dealing with. Now, if you know beforehand what the curve looks like, then you might be able to choose one of these and do a better estimate. But lots of times we just use one and go with it and say that's our pretty good estimate, because we're really on our way to something bigger in all of this. Well, an example. It doesn't take long before it's like, okay, we better get an example here to establish what's going on. So let's say you've got a particle moving along a straight path with velocity v at t equals t squared. By the way, this is close to parabolic motion. So this is really close to having actual applications in physics. But we keep it simple for the first example and just make it v at t equals t squared, where t is greater than or equal to 0. Now, if v is measured in meters per second, that's just going to give us some units to use as we go along here. It says estimate the particle's distance traveled in the first 3 seconds. Now I'm going to do this problem twice. I'm going to do it once pretty quickly to get the feel for what's going on. And then in the middle of all that, if you're like, where are you getting these numbers from? Just relax. Then I'm going to go back and do this question again in a separate program, and then hopefully break down the little pieces so that you feel confident to do it yourself. So for this example, we'll use MRAM. There's no reason for that choice here. There's no something I know about the problem to say, okay, let's use MRAM. It's just a way to practice one of the methods. And then maybe in a later example, I'll try RRAM or LRAM. You know, I'll do the other ones as we go along. And we established that we're going to use delta t equals a quarter. What does delta t equals a quarter mean? It just means that each of the rectangle will have width 1/4. Is that small enough to make a good estimate? Well, I don't know. We'll just try it out and we'll see what's going on. So here's the picture of what's going on. And this is just a general picture. It's not good enough to actually use to set it up and do the calculations yourself. But I just want you to get the idea the first time. So if that was my picture with length 1/4, well, okay, let's just make sure that makes sense. If the lengths are 1/4 and we're doing the first 3 seconds, I'm breaking it into delta t's of 1/4. That would mean there'd be 4 delta t's in each section for 3 sections, so then 12 rectangles. So there they are drawn there, and I hope you can see the MRAM, that the rectangles hook up in the middle of the rectangle. They cross the curve in the middle of the rectangle. Why is that so important? Well, okay, you'll see when I break this example down. So the base of each rectangle is 1/4, and the height of each rectangle is found by evaluating v at t at the midpoint of the interval. That's going to be the hard part, to come up with those numbers. Well, not that hard. Once I show you how to draw the picture, hopefully that'll go pretty easily. So the sum of these rectangular areas is, okay, if this blows your mind, that's okay. Don't worry. I'm going to go back and do this question again. Oh, wow. All sorts of stuff missing there. Let me get my pencil out here. This should be 1/4 times 1/8 squared, 1/4 times 3/8 squared, 1/4 times 5/8 squared, 1/4 times 7/8 squared, all the way up to 1/4 times 28 squared, and then 1/4 times 23/8 squared. And apparently when you type that all in your calculator, which is going to be a major challenge in all this, you get 8.98. Now, where do all these numbers come from? Well, okay, the first time through this, in the fast version, what I really want to see is that each of these is base times height, or length times width, either one. So that's base and a height, and base and a height, base and height. Every single time, these are just rectangles, okay? And the base every time, notice the base every time is 1/4. which is what we said our delta t would be. So one thing we need to establish, first of all, when you're adding up all these rectangles, is one part of this calculation is going to be pretty easy, is to come up with the base of each rectangle. So finding the height of each rectangle is going to be a little bit more of a challenge, but the height of each of these y values each come from this equation, which is v equals t squared. And that's why those heights are always something squared. The confusing part is where 1/8, 3/8, 5/8, 7/8, all the way up to 23/8 comes from. That's the part I got to explain in the other example. So I'm going to set this all up again in another picture here. Let me just switch over to this program here, OneNote, where I can make my own pictures and so on. Okay. It helps to draw a big picture when you're first doing these. And you may not want to draw all the rectangles because it won't take long. For me, it usually takes 3 rectangles before I go, I've got the pattern of what's happening here. Okay? The other thing I find really helps is if you draw the curve to really take off in a hurry, like really exaggerate the curves. It just makes me able to see things that's going on a little bit easier. So here's my curve. And I'm going to do as I promised. I'm going to make this curve really take off quickly, up like that. Okay? Then I want to establish the delta t's along the bottom. And as promised, I'm only going to do 3 of the rectangles. And I'm hoping that after 3 rectangles, you're like, okay, I got it. I got the pattern. You don't need to draw any more rectangles. So the first rectangle I'm going to draw is 1/4 wide. So that means the x value that I want here is 1/4. So, but the rectangle I'm going to draw apparently has to go through the curve at the midpoint. So that midpoint where that thing matches up right there is not 1/4. It's halfway between 0 and 1/4, and halfway between 0 and 1/4. Okay, well, let's see. Instead of 1/4, I'll think of it as 2/8, and so the halfway point there would be 1/8. So this point on the curve, and remember, this curve is v at t equals t squared. So this halfway point on the curve has coordinates 1/8, and then sub that 1/8 in, and I get 1/8 squared. So my area under the curve, here it comes. First rectangle, width 1/4. Width 1/4. And its height is evaluated halfway in between because it's MRAM, and so its height is the y value there, which is 1/8 squared. Now, if you sort of get that, the rest is very repetitive. If you're having trouble with that, don't worry, I'm going to do it a few more times here. Next rectangle. So if that one was 1/4, then I've got to go 1/4 again. So that was 1/4. Now this is out to 2/4, and I want to draw my rectangle through the halfway point there. So it's halfway along. There's my MRAM, because I'm going the middle of the rectangle. And what would the y value there be? Okay, so that point there was 1/8 squared. What's halfway between 1/4 and 2/4? Well, I think of it as 2/8 and 4/8. So halfway between would be 3/8. So this point here is 3/8, comma 3/8 squared. Where am I getting the 3/8 squared from? I'm just taking the 3/8 x value and subbing it into the equation to get the y value, which would be 3/8 squared. Well, not the y value, the v value, but it helps to think of it as y values for now. So my next rectangle then would be 1/4 times, that halfway point there is 3/8. 3/8 squared. And for lots of people, once they get that second rectangle, they've already got the pattern. I'll do one more, trying to establish that with 3 good rectangles, you'll be able to get the rectangle to the pattern to write this all out. So, one more rectangle. So again, I hope the second rectangle helped you a little bit, and now I'm going to do a third rectangle. Next section. Each rectangle is 1/4 wide. So my next section goes up to 3/4. That makes that rectangle 3/4 wide. Where does it hook up with MRAM? In the middle. So here's my MRAM rectangle right there. And that point right there would be halfway between 2/4 and 3/4, which would be halfway between 4/8 and 6/8. So this is 5/8. And so that y value off the curve, I know it's a v value, but that point right there is at 5/8, 5/8 squared. Where did I get the 5/8 squared? Well, I just took the 5/8 that I decided was my x value, my t value, and I subbed it into the equation, and I went, oh, 5/8 squared. So that point there is 5/8 squared. Now I'm ready to find the area of that third rectangle. The third rectangle is 1/4 wide, and its height is 5/8 squared. Each of these rectangles is just base times height. And like I say, me personally, once I can get that third rectangle drawn, then I can establish the pattern. And so then after that, it's 1/4 times 7/8 squared, and then 1/4 times 9/8 squared, and then 1/4 times 11/8 squared. And I'm going to do them all here, but I hope to do something at the end that makes you go, oh, I see where to end. See, I'm going to put an ending value out here of, they wanted from 0 to 3 seconds along here. So there's a total of, see, that can help you too, is that knowing where the last value is. I don't want to go past 3 seconds there. Okay, so that also, how many rectangles? This will help too, is that if each one's width 1/4, and I want to go for 3 sections, then I need 12 rectangles. On my page here, I've wrote out 6 of them, so I got to write out 6 more. 1/4 times 13/8 squared, and 1/4 times 15/8 squared, and 1/4 times 17/8 squared, and 1/4 times 19/8 squared, and 1/4 times 21/8 squared, and 1/4 times 23/8 squared. All that stuff. Okay, and my last one, because I just counted the rectangles, was 23/8. Well, there's another way to know. Like 3 is how many eighths? That's 24/8. So that makes me say that 23/8 is up to the last one. 23/8 would be the midpoint of the last rectangle along there. So there's 2 ways to know when to stop doing this pattern. Well, I probably get that you're looking at that and thinking it's a total nightmare. But I want you to think of this the same way that the way differential calculus started out. Differential calculus started out with 2 to 2.1, 2 to 2.01, 2 to 2.001, and then our methods got refined from there. So when you see this big mess, please know that you're putting some work in with a giant payoff. There's a giant payoff coming, and it's only a couple of lessons away. It does not take long to get the giant payoff. For now, you've got to do this work on the rectangles to really establish the base knowledge you need to move on from this. One of the things I need to tell you, though, is typing this in a calculator is a giant, giant mess. So, to be able to type it in our calculator well, I suggest not typing it into your calculator right away like that. I suggest doing a little common factoring, because there's a lot common to all of these terms, and it'll make typing in your calculator less of a nightmare. Start off by common factoring out the 1/4, because there's 1/4 in all of them. And if you look carefully, actually there's a 1/8 squared in all of them. Each one of them has an 8 in the denominator, and that 8th is squared. So I can actually go 1/8 squared and take that out of each of the brackets. And once I do that, once I'm left with in the brackets is 1 squared plus 3 squared plus 5 squared plus 7 squared plus ... all the way up to 23 squared. While that's not a lot better to type in your calculator, well, sorry, that is a lot better to type in your calculator. There's no question that's a lot better. Now, it's still a lot to type in your calculator, but comparatively speaking, you're not typing in each of these terms with all that stuff in there. So I've common factored out a 1/4 out of each of one of those terms, and then I've common factored out a 1/8 squared as well. You could even simplify that first term a little bit, or that first multiplier a little bit if you wanted. So then I want to type that into my calculator and make sure I get the answer that was on the screen there. So let me bring up a calculator here. that sort of has the features I want. This one here. I hope this resembles a lot of the calculators maybe that you have out there. And so what did I have? I had where's my fraction on this one? 1/4. And then I got to push off of that. Where's my arrow on this one? There's my arrow. And then there was a 1/8. And again, if you do better on that, simplifying that before you type it in here, that's fine. But I didn't bother here. 1/8, and then open a bracket for the for what's in the brackets there. 1/4, 1/8 squared. I'm just checking to make sure I did it right. And then I got to do in the brackets. I got to go 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared plus 13 squared plus 15 squared. Okay, halfway through typing this in, you're like, Mr. Todd, I really hope you've got something better up your sleeve coming soon. And I really do. So just please struggle through this typing in for just this lesson and maybe part of one more lesson, and then we'll come up with something better. 21 squared plus 23 squared. And I got talking while I was doing that, which is a giant mistake. You really should focus when you're typing these things in so you don't make a mistake in there, because there's nothing more nightmarish than trying to find these mistakes. Now, on calculators like this that have this nice scrolling display, though, it is sort of nice that if you do have a mistake in there, it's not hard to look back over and make sure you typed it all in right. And there I get that 8.98 that you saw in the PowerPoint. Okay, so really think about making some clever common factoring to save yourself a lot of work on the typing in of your calculator. And draw a picture, a really big picture, to get the first few rectangles to establish the pattern of the numbers here. I promise there'll be a pattern every time, and it won't take long to establish that pattern. Okay. Therefore, the particle moves approximately 8.98 meters in the first 3 seconds. Sort of cut off there because I had to write all over that thing, but you can see that there's your statement there. So 8.98 actually is an extremely good estimation. You can imagine in your brain that's like, oh, well, maybe it's the actual answer here is 9, and you would be right. We'll find out later that that 9 is the exact answer, like exact answer. So you can see 8.98. You might imagine moving forward, I'm really jumping ahead here, that if you, instead of using the 12 rectangles we used, if you went to 20 rectangles or 30 rectangles or 40 rectangles, you'd see this area go 8.98, 8.99, 8.999, and do the same thing that happened in differential calculus, that it would approach some value. And that's exactly what happens. To totally give it away, that's exactly what's going to happen here. But for now, we've got to lay the foundation and get good at these basic ones first, okay? So, 3 more examples. Solve the following 3 examples on a separate page. I'm only going to do 2 of them online here because the last one, 1B, you can see says use a calculator program, to which you're like, area with 1,000 subintervals, that might be freaking you out. Well, I'll show you in class or in person, or I'll make a separate video if it comes to that. But for today, we'll just say, okay, the calculator program one, we'll see that afterwards, after we practice the by hand versions of this ourselves. So I've only got a couple of examples actually to do. I've put those on a separate page here. I think I got them somewhere. Do I? Yeah, here we go. Yeah. And I don't need that keyboard there. Okay, so here we go. So here's a much more complicated function, and I'm going to go through the steps here to try to do this one. Okay, so this time the graph is f at x equals x squared sine x. We jump away from physics a little bit to go, okay, let's make this a pure area problem and not worry about the distance, velocity, time thing. And they say on the intervals 0 to 3, shown below, use LRAM with 9 subintervals to estimate the area under the curve from 0 to 3. Well, let's really break this down and slow it down a little bit. If there's 9 subintervals over 3 seconds, that means that each subinterval should be 1/3 wide. I literally just take the 3 that I see here and divide it by how many intervals, and I get a width of 1/3. So when I go to draw my picture, I want each rectangle to be 1/3 big. Now, this picture that they've given here is off a graphing calculator, but I'm going to draw a much bigger one for me to use, right about there. And as promised, I'm going to draw this curve, really exaggerate it, like really make it take off like that. And is that a good approximation of that curve in the first part? Well, no, but I'm only just trying to do a visualization of the whole thing. Okay, and I'm going to try and do the first three, and hopefully after three, I'll have established such a beautiful pattern that we can write down all the other rectangles without drawing every single rectangle. Now, great news here, and one of the advantages of LRAM is sometimes LRAM, the first rectangle, is really simple. So let me draw 1/3 on there. And when I'm using LRAM, do you see this rectangle will just be right along there because it connects up at the left side there, and there's my rectangle there, completely flat. And so this value of the left-hand side here, and I'm going to draw it over here, will be 0 is the x value, and when I sub it into the function, I get 0 squared sine 0, and you might be like, well, that's 0 anyways. I know, but see, the only reason I'm drawing these three rectangles is to establish the pattern of numbers. So I just leave it as 0 squared sine 0. I know that's going to be overkill typing in the calculator, but it's going to help me to draw the other rectangles. So the next rectangle should go from 1/3 up to 2/3 because each rectangle has width 1/3, and it hooks up on its left side. So it's right there at 1/3 and over to there. There's my next rectangle. You can see a massive underestimate here. Maybe my diagram is exaggerating the overestimate too much here. But for now, again, we're just trying to do an estimate. So the important thing is to get that height of the rectangle here. So how would I get its height? Well, it's x value 1/3. And when I sub 1/3 into the function, I get 1/3 squared sine 1/3. And then I'll draw the next rectangle, which would be at the 2/3 mark and would go out to 3/3. Now you can draw more rectangles if you want to establish the pattern. But let's just see if I just do those three rectangles, whether I'm right, whether it's enough to establish the pattern of what's going on here. So we need this point here, which is now 2/3. You can see the x value at the bottom there. And then when I sub 2/3 into the function, I get 2/3 squared sine 2/3. Okay, so here comes my area. First rectangle, base 1/3, height 0 squared sine 0. And I've used brackets there that are sort of unnecessary, but I did it to really try and visualize the pattern that's going on here. Next rectangle, width 1/3, height 1/3 squared sine 1/3. And maybe you're already like, I already got the pattern. I don't need any more rectangles here. Once I have that, see, some people are like that. Once they have the second rectangle, they're done already. But I like 3 just to really establish it. Next rectangle, 1/3 is the base. The height is, oh, I made a little mistake in the previous one. I said the right thing and I wrote the wrong thing. I got so wound up there. Let me just fix this. This was 1/3 squared sine 1/3. 1/3 squared. So 1/3, and then the height is 1/3 squared sine 1/3. Let me highlight those up there so you can see them. There's the y values right there. So next rectangle, 1/3 is the base, and the height is that y value up there. It's 2/3 squared sine 2/3. Okay, so without drawing the next one, I can already see what the pattern is going to be. It's going to be base 1/3, and then its height is going to be 3/3 squared sine 3/3. And you might be thinking, well, 3/3 is 1. Shouldn't I just write 1? Well, no, to establish the pattern and write them all out, you probably want to write the whole thing out. Now, once you've got the pattern, it's easy to write out the next ones. The only important thing is where to stop. And I say go back to this 0 to 3 and say, okay, well, I got to go out to 3, which is equal to 9/3. I can't go up to 9/3. My last rectangle is going to be the rectangle that goes from 8/3 to 9/3. That's one way to think about it. The other way to think about it is to go, well, I've got 9 subintervals. That means 9 rectangles. I got to keep going until I have 9 of these. And let's see if that all works out. How many do I got so far? 1, 2, 3, 4. I've done 4. Okay. So next one. 1/3. And it's 4/3 squared sine 4/3. Then 1/3. 5/3 squared sine 5/3. Then it's 1/3. 6/3 squared sine 6/3. Some calculators, you're going to want to put that what's in the sign in a bracket, so I'll just keep doing that. Then 1/3. 7/3 squared sine 7/3. And I got so into writing these things that I forgot to keep counting them. So let's count them again. 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Oh no, I needed 9 of them. 1/3. 8/3 squared sine 8/3. And that's the last one. There's 9 of them. But you can see why it is the last one, because my last rectangle would start at 8/3 on its left border and end at 9/3, and that would cover the last area there. Now, this is a giant nightmare. In fact, my calculator that I try to do this in and type it in, just like you saw here, just to check my math, when I typed it in there, it was too many things to type in. My calculator stopped and wouldn't let me type anything more in. So the common factoring move is huge here to really pull out of all this thing. So really look at this for a minute and see what's in every single bracket here, or see every single term. Every single term has a 1/3. Then every single term has a, right there, look right there. See, it's got a 1/3 squared. We got, every term's got a over 3 squared. So I'm going to pull that out and make it 1/3 squared. And that'll really shorten down what I have to type into each of these brackets. For instance, all that's left of this first bracket is, or this first term is 0 squared sine 0. And all that's left of this second term, when I pull that out, is 1 squared sine 1/3. And then the next term is 2 squared sine 2/3. And the next term is 3 squared sine 3/3. And then 4 squared sine 4/3. And then 5 squared sine 5/3. And then 6 squared sine 6/3. And 7 squared sine 7/3. And the last one would be 8 squared sine 8/3. Now you see how much less time that took me to write. I mean, it's still a giant nightmare. Don't misunderstand. I know how big a nightmare this is, but it was a lot nicer to type all that stuff in than it was to type the previous one. So putting in your calculator obviously is going to be a lot nicer when you're doing that. I'm just going to scan over them to make sure I like them all. 2 squared sine 2/3, yeah, because the 1/3 squared. 3 squared, so you might take a little time to stare at that to make sure I've taken everything out that I need there. So I'm going to go over to my calculator. Where is it here? And I'm going to try and type that mess in. So what did I have? My common factor was 1/3. And you could tidy this up a little bit, but I'm not going to, because I really want you to see where these things are coming from. And then I saw that in every term there was a over 3, a denominator of 3, and that was squared every time. And then within the brackets, what was left was I see that this calculator is in degrees, so I've just flipped it over to red. Oh, that's nice on this calculator. I just hit that button and it switched over to red. Okay, in radians mode. Okay, let's see. First term, 0 squared sine 0, close the bracket, plus 1 squared sine 1/3. Oops. Then 2 squared sine 2/3. Oh, this calculator is cool. Look at, I think it's giving me the answer, a running total there. Watch, look, it says I press this. Interesting. All right. I got to stay focused here. It's easy to make mistakes here if you don't stay focused. And that's a big problem for me, is staying focused as I type these in. Plus 3 squared sine 3/3. Doing that every time, forgetting that arrow there. Plus 4 squared sine 4 sine 4/3 plus 5 squared sine 5/3 plus 6 squared sine 6/3. I'm almost there. 7 squared sine 7/3. I like how that looks, so I'm just going to fix that. 7/3. And finally, 8 squared sine 8/3. Close that bracket. Close the bracket for the whole thing. Press equals. My calculator was calculated as I went there. I don't think I don't see any handheld calculator that does that. So that's what's neat on the iPad here. I've never seen that before. Okay, and so I get a total of 5.490425. You know, some monstrous crazy number there. Back to my answer here. 5.49042552. 52, I think, something like that. Wow. Yeah, that's a lot of typing. And that common factoring is vital, because some calculators will totally choke on that. You won't be able to write all that stuff in. I mean, you could press equals, then hit plus, and most calculators will go answer plus, and then you can keep typing after that. But I think even from that was a nightmare enough to type it in as it was. I think you're going to want to do that common factoring. So next example, use a calculator program to estimate the area with 1,000 subintervals. On the Casio FX9860G2, the calculator we use in class, there's a way to put a program in there that will do this for you automatically, and you can do 1,000 subintervals pretty easily. I'll show you how to do that in class, okay? So that means the last question, number 3, is a calculator program here. So this is our last example here. A particle moves along a straight line with velocity v at t equals 2t cubed. V is measured in meters per second. Use RRAM and 10 intervals to estimate the particle's distance from 2 to 4. This thing does two things. It wants you to practice out RRAM, and it also wants to practice not starting at 0, starting at 2. So we've got to keep track of those two things. I've left lots of space here. So here comes my big picture of what's happening here. If you have trouble drawing these, go big, like maybe even half a page when you go to draw these. So I'm trying to do the velocity, do the distance from 2, and I'm going to put 2 way over here. And then I'm going to do as promised. I'm going to draw this curve, and I'm really going to take off right at the start because it helps me to draw those when I really take off like that. So I'm just going to give myself a little more space there, like that. So they want RAM. So we really got to talk about this. It's from t equals 2 to t equals 4. So there's, how long? We're going delta t of 2 seconds. Maybe I won't call that delta t because that might confuse you with the other delta t that was done in another question. But anyways, 2 seconds, and they want 10 subintervals. So each of these delta t's then, we want to take that 2 seconds and divide it into 10 subintervals. Our delta t is 1/5. We got each of these rectangles has got to be 1/5 wide. So that means my next point on this axis down here will be 2 1/5. Well, I'm going to switch over to fifths for both of these. So this 2 here is 10/5, and now I got to go 1/5 more over. So this is 11/5 to get my first rectangle. And they want RAM. So they want the rectangle hooked up on the right side of the rectangle. So there's my first rectangle right there. And it's evaluated at the 11/5. Notice that with this increasing function, then we're going to get an overestimate right off the bat here. And now you can do this several ways. Notice I wrote 15ths down there, and it's not 15ths, it's fifths. You can do this several ways where you draw all your 3 rectangles first. And it doesn't have to be 3, by the way. Some people, after 2 rectangles, are like, I got it. And some people need maybe 4 or 5 rectangles to really establish the pattern. But you can do the rectangles first and then do the areas afterwards, or vice versa. I'm going to slow it down and do the individual rectangles one at a time, because I think I did the other one where I drew the rectangles first. So this point right here is 11/5, and the v value, or the y value, sort of thinking this way, the height of the rectangle, I find by taking that 11/5 and putting it back into the original function. So that's 2 times 11/5 cubed. This allows me to do my first rectangle. My first rectangle is 1/5 wide, and its height is 2 times 11/5 cubed. How many rectangles do I got? Okay, so 10 rectangles this time. But I'm only going to do a couple just to get the pattern going. So next rectangle, instead of 10/5, that's 11/5, I want 12/5 will be the next check-in point. And so I want to do RAM. That's what they asked for, was RAM here. So I'm hooking up the right side of the rectangle here. So I'm evaluating at the right. The rectangle hooks up to the curve on the right side there. And this point here then is 12/5, comma 2 times 12/5 cubed. So now I've got my next area. My next area is width 1/5. The rectangle is 1/5 wide, and its height is 2 times 12/5 cubed. And again, if you're like, I totally have the pattern already, I don't need a third rectangle because I can see what's going to happen, great. I find the third rectangle really brings it home. I go, okay, one more rectangle hooked up on its right side here. And this will be 13/5. And so this point here will be 13/5, comma 2 bracket 13/5 cubed. And all I've done is taken that 13/5 and put it into the equation for the v value or the y value, whichever way is easier for you to think about. And it's the equation's 2 times t cubed, so I use 2 times 13/5 cubed. So next rectangle, width 1/5, height 2 times 13/5 cubed. And hopefully by that point, you've got enough to do your rectangles. Now, 2 ways to know when to start. I want to go all the way out to t equals 4. So I don't want to go, my last value in RAM, I'll be hooked up at 4. My last value should be 4 in RAM. So that would be 20/5. So the other way is just to count the rectangles. I've done 3 rectangles here. I'm going to go again. 1/5 times 2 times 14/5 cubed. Then 1/5 times 2 times 15/5 cubed, plus 1/5 times 2 times 16/5 cubed, plus 1/5 times 2 times 17 fifths cubed plus 1/5 times 2 times, oops, I did add there. Funny how that can happen. I actually said times and wrote add, weird. 18 fifths cubed plus 1/5 times 2 times 19 fifths cubed and 1/5 times 2 times 20 fifths cubed. Now, I know I'm done for two reasons. One is that's 10 rectangles, and I know that we wanted 10 subintervals. The other way I know is with RRAM, the last one will be this value here. With LRAM, it was one short. With MRAM, it was really weird, right? So it just depends on the method you're using. And I've done one of each in this lesson. I started with an MRAM and then did an LRAM, then did an RRAM. Typing that into your calculator would be a giant nightmare. It's going to be a giant nightmare anyways, but I can make it better by doing some common factoring. I see in each rectangle, there's a 1/5, there's a 2, and even better, there's a 1/5. My screen's freezing for a second here. Well, 1/5 times 2, and then there'll be a 1/5 cubed pull out of each of there. If I can get this to unfreeze, then I'll keep going here. There it comes. 1/5 cubed. You see, each of those fractions, I know it's 11/5 cubed, but there's a 1/5 cubed in there. And then in the next one, it's 12/5 cubes, but there's a 1/5 cubed in there. And so I'm pulling the 1/5 cubed out every single time. And you could simplify that leading term if you wanted. I don't usually. I just leave it as it is. And then so what's left? I'd get 11 cubed plus 12 cubed plus 13 cubed plus 14 cubed plus 15 cubed plus 16 cubed plus 17 cubed plus 18 cubed plus 19 cubed plus 20 cubed. And even that's a nightmare, but I hope you agree, boy, it's a lot better than what I just did there. So now I go to my calculator. Where is it? There it is. And I go again. So what was the common factor? 1/5 times 2 times 1/5 cubed. And then in the brackets was 11 cubed plus 12. Oops, something went wrong there. Was out front was a 1/5. And then somehow I got out of position here, so let me go back over here. Power 3 plus 13 cubed plus 14 cubed. I did it again. Oh, all gone. Okay, start again. Let's see. Common factor, 1/5 times 2. And then the other common factor was 1/5 cubed. And then in the brackets, 11 cubed. Oh, I see a cubed button I can use in here. Plus 12 cubed plus, oh, that's way better, 13 cubed plus 14 cubed plus 15 cubed plus 16 cubed plus 17 cubed. What am I trying to get to here? 20 plus 18 cubed plus 19 cubed plus 20 cubed. Close brackets. Now let's just check all that before I hit equals. 1/5 cubed, 11 cubed. I like it. Looks good. 131.44. Back to here. Area is 131.44. Well, that's the area. Now, this question was a physics question, so that's really the distance. Therefore, the distance traveled was 131.44 meters. And I'll just put over here approximately. It's not really clear yet how good an estimate this really is. You can saw from my pictures that I was overestimating the area a lot there. So we'll work on how good at estimates these are. Okay, so don't do anything with a calculator program yet. It'll be good enough to practice the ones without the calculator program. So if it says LRAM, MRAM, RRAM, then you do it this way. And if it says use a calculator program, well, I'll have to show that in a separate video. I'll see if I can get that rigged up on a computer and get that program to work on a computer. I'm not sure if I can, but I'll give it a try. If not, we'll do it in class. Okay, let me know what questions you have. I know this is a long procedure, but I guarantee you we're laying a foundation for something extremely important.